We propose a new adaptive imperceptible pattern projection algorithm that considers parameters of human visual perception. Linked with real-time flash keying, this enables in-shot optical tracking using a novel dynamic multi-resolution marker technique. This enables the correct integration of three-dimensional objects and virtual backgrounds in the projection. A synchronized camera captures every single frame at a speed of 120 Hz. The embedded code can be reconstructed from 2 consecutive frames. We integrated two-dimensional markers for optical in-shot camera tracking. To determine the maximum non-perceivable delta values for embedding the code, a user test was carried out. Subjects were seated in front of a back projection screen displaying differently scaled patterns with integrated codes. To force a constant eye movement, subjects were ordered to follow a moving point with their eyes during the test. The just noticeable differences for delta values were measured for varying resolutions and luminance. The results were used to derive a function to calculate the optimal non-perceivable delta values for arbitrary images and codes. The quality of the calculated function was validated in a user evaluation. While no significant difference was measured between the quality of no integrated code and the calculated delta values, the perception of integrated codes increased rapidly for greater values of delta. These subjects also did not recognize any significant difference between a projection without integrated codes and a projection with integrated codes using the proposed temporal blending technique. Our current prototype of a TV studio mockup consists of an off-the-shelf stereo-enabled DLP projector displaying arbitrary and dynamic content at a speed of 120 Hz. The camera system consists of 2 optically aligned CCD cameras. For real-time flash keying, a dimmable white LED illumination system is used. A custom synchronization electronic device picks up the shutter signal generated by the graphics card of the PC that triggers the stereo projector. This signal is then used to trigger both the camera and the illumination system at 120 Hz. Instead of a constant illumination, the scenery is illuminated 60 times per second by short flashes that are synchronized with the projection of the cameras. 2 consecutive captured frames contain the illuminated foreground in one image and the unilluminated foreground in the other. This allows one to separate the foreground from the background on a per-pixel basis. Due to their high frequency, the flashes are not detectable. This sequence shows the performance and quality of real-time flash keying. While the moderator is illuminated and keyed, the background is overlaid with a virtual video texture and a 3D object. To ensure continuous tracking despite partial occlusion, differently scaled markers are embedded into the projection in an optimized way to increase their visibility. We determine the visibility of each projected pixel from the camera's perspective. This results in a new marker image that contains a set of optimally scaled and placed markers with respect to foreground occlusions and camera perspective. To keep the visibility of the embedded markers at a minimum during code transitions, we use a temporal blending technique for each exchanged marker.